Good to see you.
Oh,
I'm just wondering because you
hey man,
purposefully
good to see you.
I had a good
set it
meeting,
up to
good
the
lunch
stage.
with your students today. It was a lot of fun.
Cool, cool. Yeah, I look forward to dinner.
Great. So, take it away.
All right, welcome everyone to another EECS Colloquium. Today our speaker is Bruce Maggs. He received all of his degrees and a postdoc from MIT, and after graduating from MIT, he spent some time as a research scientist at NEC Research, and then moved to Carnegie Mellon, where he spent quite a bit of time before moving to Duke University as a professor in computer science. While he was on leave from Duke, he helped to launch a small company that you may have heard of, Akamai Technologies, serving as its first vice president for research, and still there part-time as the vice president for research. His own research, of course, from that affiliation, you would guess, is in networking, distributed systems, and security. He's received many awards and recognitions for his work, including the NSF National Young Investigator Award, and he was also the first co-awardee of the Daniel Slotnick Award for the most original paper in the International Conference on Parallel Processing. Please join me in welcoming Bruce Maggs.
All right. I grew up in the Midwest, and like every Midwestern boy, I thought that someday I would end up in California because on television, California seemed like the ideal place to live. Mostly I was watching the Beverly Hillbillies. So somehow I don't get out here. I got stuck on the West Coast, but I always enjoy coming to visit Berkeley, and I have many friends here. And I'm actually slightly partisan about the issue that's maybe on all of our minds. So I want to present you with one of my favorite quotes. I was at Carnegie Mellon for 15 years, and I developed an interest in the life of Andrew Carnegie. And I read several biographies, and one day I came across an interesting quote. This is what Andrew Carnegie had to say about the issue. This was written in 1901 in a letter to Andrew White. So, by the way, I once showed this quote at Stanford, and there was stunned silence. But now I'm getting stunned silence from you guys. I expected to maybe get a little more enthusiasm. So I'm going to talk today about some work that I've been doing with a number of colleagues. Bala Chandrasekaran just finished his PhD at Duke, and he's going to Technical University of Berlin as a postdoc. Nadi's a grad student at Duke in the computer science department. Anthony and Greg are astronomers, but they have a side business where they consult for companies that are building low latency financial trading networks. And we'll talk about that in a little bit. Brighton, I think many of you probably know, he's one of your favorite former PhD students here. He's now at the University of Illinois. And Ankit, who's Brighton's former student, who has just started at ETH in Zurich. I think this is going to be a fun talk, but I have to warn you that it's not your usual talk where I just say, okay, here's the latest research I did. So this is partially a research talk, but it's also partially a challenge to the networking research community and to the networking industry. And it's also maybe partly preaching to the choir. But it's a fun project because we have a manifesto, okay, which I call the Speed of Light Manifesto. And this is it. The internet should operate at the speed of light. What I mean by that is the time it takes to send a packet from point A to point B on the surface of the Earth should be as close as possible to the time it would take light to travel that same distance. Now, we're probably not going to achieve that, but it's nice to have a clean statement of what the goal is, and it's a statement that you can measure against. You can ask, how close are we today to achieving that? And I think that you could go a little farther than this and say, look, I don't want to just send the data. What if I need to access some simple service somewhere? the time it takes for me to send my request and get the response back should be close to the round trip time at the speed of light. Okay? And we're not going to do any better than that. At least, apart from some crazy schemes where you send neutrinos through the Earth, we're not going to do better than that. So here's a toy experiment. Let's get started trying to understand how fast is the internet today. Ankit performed this experiment from the CSL building at the University of Illinois. He used a command line tool to fetch the first 20 kilobytes of a web page called theoatmeal.com. I have no idea what that is. From a web server, and it turns out that that web server is in Oregon somewhere. And the time to do that was 430 milliseconds. Then he did another simpler experiment where he sent a single ping packet, an ICMP echo request, waited for the response, measured that. That took 55 milliseconds. So let's ask, for those two things, those two tasks, how close was that to the theoretical limit, the round trip at the speed of light? It turns out that the round trip distance is 5,700 kilometers, and that's 19 milliseconds at the speed of light in vacuum. And so what that means is that for the task of fetching 20 kilobytes from a web page, and that's a tiny amount of data, bandwidth is not a consideration. That didn't add anything. We're 23 times slower than what we would have achieved if that could have been done at the speed of light. And you can see also that the 55 milliseconds for sending a single packet back and forth is about 3 times slower than the speed of light. And that number 3 will come up again and again. That's roughly the infrastructure cost. And then the reason we have a 23 here is because what we'll see, it's the network protocols that are just killing us. Okay, so let's do a larger scale experiment. The next thing we did was in 103 different countries, we went to Alexa and we found the 500 most popular websites for each of those countries. And then there are about 28,000 of them that are distinct because many sites are popular in more than one country. And from 186 Planet Lab locations, which are generally servers that are well connected, they're on high-speed networks, they have high-speed connections, we went and we downloaded the first, I think, 20 kilobytes of each of these pages, and we recorded the latency, and we knew where the Planet Lab servers were located. We used off-the-shelf geolocation tools to locate the web servers, the ones we were fetching the content from, and we asked, well, what was the inflation over the speed of light latency? And we get a curve that looks like this, and the median inflation was a factor of 35, all right? So roughly speaking, what this is saying is that when you click on a link, the time before you see anything is about 35 times longer than it takes just for the information of the request to travel to the web server and then for the response to come back. That's kind of a nice number in the sense that it means there's plenty of room for research, right? We got a lot of angles that we may be able to attack here. And we're going to look at some of the causes of this and then some of the things we might be able to do to address them. So I want to talk a little bit first about motivation, okay? Sometimes when I present this talk, people say, the internet's fast enough already, okay? Are you kidding me? Do you guys drive minivans? That's not fast enough for me. I think it's slow, but that's not really a convincing answer. I think the convincing answer is, well, there are people who can tell you we really want it to be faster. So what's the low-hanging fruit? What is the application that would immediately benefit from, and I mean benefit in the sense of make money, from a faster internet? Some people, if you've read Michael Lewis's book, Flash Boys, you'll say, oh, financial trading. Okay, that's too easy, but yeah, that's true, although I'm not really targeting financial trading. Those guys, and we'll talk about it, they're already doing this, but in sort of very specialized routes. No, it's something that's more near and dear to my heart. It's electronic commerce websites, okay? So there have been a bunch of studies by Amazon, by Google, by Microsoft that show that if you can shave tenths of a second off the delivery of a web page, it translates to measurable increases in all its profits. It's sort of a dirty secret that if you look at the bytes that are delivered by a content delivery network, like between video and large software downloads, that's probably 70 to 75% of the bytes. There's no profit there because that's not latency sensitive and it's kind of commoditized. The money comes from being able to reduce the latency in e-commerce websites and having an advantage by having put servers in thousands of locations around the world. So you can do that. It's orthogonal. You want to get the servers as close as possible to the users, but you'd also like to make the network as fast as possible. So that's the low-hanging fruit. There are other applications you can imagine. We mentioned financial trading, games, remote collaboration. Latency is critical there. So my kids, we share a man cave, my two 15-year-old boys and I. And we don't talk because they're wearing headsets and they're playing Counter-Strike Global Offensive. They only talk to me when they think there's something wrong with the network. They say, "Dad, our network sucks." I'm like, "Guys, don't you know I'm a networking expert? We've got 10 gigabits per second throughout our house. It's got to be the server." Then they say, "Akamai sucks." Yeah, they're hard on me. But so also, basically, the interactive applications are the ones that are most likely to benefit, where there's a human in the loop, possibly where there's a machine in the loop, who knows, but certainly where there's a human in the loop, gaming, web surfing, remote surgery. Actually, I'm not endorsing doing surgery over the internet. I think we're not ready for that. But one of my favorites also is my wife is a professional musician. In fact, the reason my schedule got all fouled up was because I forgot she's giving a concert next Tuesday night. And she plays guzheng. It's a Chinese harp with 21 strings. And she tells me that she's performing a concert where she needs to play in 3 different keys, so she needs to bring 3 different guzhengs. So I have to be there to carry the guzhengs. All right, so I'm sorry, but that's why I'm a week early here. But musical collaboration over the internet, it is not possible to do this between North Carolina and Berkeley today. Real musicians just would go nuts because the latency over the internet is large enough that it would be like, what's wrong with my partner? He's a beat behind, right? So that's another, probably not a big money maker, but a real application. So here's a human perception phenomenon that perhaps makes the job a little bit easier. So it turns out that with the visual perception system, humans cannot really distinguish between an event that occurs 0 milliseconds after you press a button and 30 milliseconds after. They appear the same. So it says that if you can make the response time of something under 30 milliseconds, it's equivalent to being instantaneous, right? So that's, maybe you don't even have to make it the speed of light if you just say absolute goal is under 30 milliseconds. Other forms of perception, the numbers are different, okay? So for the ear, it's possibly shorter. For feeling, touch, it's longer. 30 milliseconds, though, in terms of the speed of light, is a long time. So if you look at, I don't know whose idea it was to say, let's just put a server in North Dakota. But if you had a server in North Dakota, you could reach all of the continental US and Alaska within 30 minutes. That's probably why it's in North Dakota, to get Alaska there. You could reach it all in 30 milliseconds, right? So that you can go a long way in 30 milliseconds at the speed of light. Anybody know what this is? I understand that's about the size of an average undergraduate class at Berkeley now. And that's a gaming convention, right? So these guys really care, right? So the way that you get good latency is you just go to the same room. Now, that's kind of the hard way to reduce your latency. But here's a kind of cool phenomenon. So if you think about the surface of the Earth, all right? Actually, I think my animation's a little out of order. Okay, from elementary geometry, you know that the area in a circle grows as the square of the radius, okay? Now, if you start to speed up the network so that the radius, the distance you can reach in a certain amount of time is growing in some, let's say, linear fashion, the area that you can reach, the surface of the Earth, is growing quadratically. So this is kind of cool. A linear speed up in the network leads to a quadratic increase in the distance you can reach. Now, the Earth is not uniformly populated with people, but we did a study where we looked at the number of people that were within 30 milliseconds at the speed of light of 200 of the world's capital cities. And then we said, okay, if we look at our network and we run it at 1/10 the speed of light, 2/10 the speed of light, 3/10 the speed of light, and so on, using population maps, how many people can you reach? And the answer is it's not growing, you know, sort of strictly quadratically as you would see if population was uniform, but it is growing superlinearly. Okay, so you get a superlinear increase in the size of a community that can be reached from one point with a linear increase in the speed of the network. And on top of that, if you believe in the networking effect, where each new member of a community adds more than one because the number of interconnections may be growing faster than that, that's just compounding this. So here's a little study we did. We were thinking about this question of how can you improve the performance of downloading web pages? And there's a tool that was developed at MIT called Mahi Mahi that lets you go visit a website and it records everything that happens, and then it lets you replay it in a simulated fashion, and you can kind of change the behavior of the network. So you can see what would have happened if the network behavior had been a little bit different. And I'm not going to go through all of this graph, but one interesting experiment that we did was we took 108 randomly chosen websites from the Alexa list of US-based popular websites, and we downloaded them, and we replayed the downloads, but this time we said, what if all the traffic that went from the browser up to the server had a reduction by a factor of 3 in latency? Okay, that's that magic number 3 I showed you in the difference between the ping time and the actual speed of light time. So if you just sped up the network by a factor of 3, what impact would this have on downloading the web page? Now it turns out that on average, if we look at these websites, more than 90% of the bytes are going down from the server to the client. Only 8% of the bytes are going up from the client to the server. But the speed at which they reach the server really matters because first there's the initial request, that matters, but then everything the server is sending is being acknowledged by the client, and the faster those acknowledgments reach the server, the faster the server's going to send, right? And if you look at this dotted green line somewhere in the middle, you see that the median is about a 20% decrease in the download time if we could just speed up the channel from the clients to the servers, right? So you don't even have to do this for most of the bytes. If you're judicious about speeding up some of the packets, you may be able to get so we got a 20% increase by only speeding up 8.5% of the packets. Okay, now there's still a bit of a mystery about this factor of 35. That it took 35 times the round trip at the speed of light to download 20 kilobytes from a web page. The networking experts here probably can immediately guess some of the reasons. And I'm just going to try to quantify that. But let me say that before we get into technical details, the real reason for this is because for the last 20 years, the networking industry has focused on one metric and one metric alone. And it's not latency, okay? It's bandwidth. If you go and you look at advertisements for internet service, they will always quote you megabits per second. If you called them up and said, okay, but what's the latency to the 10 largest cities in the world from my house? They wouldn't know what you were talking about, right? They're not trained to answer a question like that. They certainly didn't try to optimize it. And it's understandable, because the reason they had to focus on bandwidth was there was a holy grail, which was high definition video into the home, okay? And they kept moving towards that. And what's kind of timely about proposing this new challenge of a low latency network is that we've already gone past that, okay? We have high definition video. So maybe it's time to think about adding some other metrics, such as latency. You might be interested in knowing something about a trade-off between latency and bandwidth. So for many years I had DSL in my home, and they kept improving the throughput on my link. It went from like 6 megabits per second to 10 megabits per second to 15 megabits per second. Then it jumped to 30, but then I found out that's because they just put in 2 lines. Well, how did they do that? Well, they started running the data faster and faster over those links. At the same time, the latency started to get larger and larger. The first hop from my house to the first router went up to 22 milliseconds. Okay? That's past North Dakota. Why did that happen? It's because as they ran these wires at higher and higher speeds, they were having higher and higher bit error rates. So they used forward error correction. And they started buffering a bunch of packets before they sent them so that they could add error correcting codes. Right? So they didn't really care. They were willing to trade off huge amounts of latency in order to get higher bandwidth. And you know, that hopefully will go away as we get fiber to the home. Well, let's look at, in our experiments, the details of where time was spent. So there's a lot of curves here, and I'm not going to go through all of them. But let's think about what happens when you try to visit a website. The first thing is you've typed the name of the website into the address bar of your browser. You click enter, and then there's a DNS lookup to find out where that, what's the IP address, what's the network address that the browser should send its HTTP request to. And that DNS server could be anywhere. It's not necessarily co-located with the server. And then your browser will open up a TCP connection to the server. It will send it a special TCP packet that has a flag called SYN set. The SYN packet. That means I want to open a new connection. What the server does is it sends back a packet with SYN ACK, 2 more flags set, and then the browser sends back a packet that says ACK, and that's called the 3-way handshake. So what we measured first was the first 2 parts of that handshake, the time from the SYN to the SYN ACK. That's 1 round trip, and we can see here that the median delay was about 3.1 or 3.2. Okay? Same as that ping we did, roughly speaking, to Oregon. But that's actually the median. We also did pings to the servers, and the time was essentially identical to the time for the TCP SYN-ACK round trip. Then we looked at how long it took before the first bytes of data arrived after the client sent the ACK, the last acknowledgement in the 3-way handshake, until the first data arrived, the first part of the HTTP request. That's here. Okay? This took a little longer, and that maybe some of that there's a little bit of processing time. And then we look at the transfer time, the time to transfer the data. That's over here. And then this is the total time. All right. So we can kind of summarize what's going on as saying there are basically 2 causes of latency. One is there's the infrastructure. And in the infrastructure, we have a number of problems. One is the signals are traveling in optical fiber, not in free space, and you lose a factor of 1.5 right there. Second, if you look at the paths, the shortest path in fiber across the US, it's not actually line of sight. That's an issue. And third is that routing policies don't always pick even the shortest path that is available. That's that sort of factor of 3. The rest is coming from the round trips that are involved. So there's a DNS round trip, there's a TCP handshake round trip, and then TCP also doesn't allow a server to start sending data at full speed right away. There's something called slow start, and it takes a while before the server is willing to send multiple packets all at once. Okay? So it adds up to this factor of about 35 in the median. So I want to talk a little bit about this issue of routing policy. So when I teach a networking class, I often teach the BGP protocol. This is the protocol that different network operators use to communicate to each other how to reach different places on the internet. And it's really kind of a miracle that it works, because you have these competing operators and they all want to operate as cheaply as possible and only fulfill the obligations that they really have to their paying customers. And yet BGP is this glue that holds things together. And when I'm all done showing how BGP works, I say to the students, do you see where it optimized for network bandwidth? And they're like, no, there's no place in there. I say, what about latency? No, it's not in there either, right? It's a dirty secret of internet routing that there's no effort to give the end user good performance. It's just not in there. It's 100%. Let's make sure it costs the operators the minimum amount of money. And so they don't always take the shortest path. So here I'm going to show you the path taken when there's a client in Warsaw, Poland, who wants to access a server in Warsaw, Poland. Okay? You can imagine what's coming, right? So the client's traffic, he's sending the request to the server. It first goes to Frankfurt, then comes back to Warsaw. And then the server has to send a response, and the response goes to Frankfurt and then back to Warsaw. Okay? So that's hurting us. That's an extreme example because they're in the same city. But we're ending up losing like maybe a factor of 1.5 or something on average because of this kind of issue. Okay? So in my curve here, I didn't talk about it yet, but there's a blue line here. And what we did here was we looked at a trace route that goes to from a source to a destination. And we geolocated as many routers as we could on the trace route. And then we said, okay, let's say that you were stuck with this path, but you could go at speed of light from each hop to the next along a line of sight path. How would that compare to the true line of sight path between the 2 points? That's sort of saying, if you look at the path that was taken, the actual physical distance that it traveled, how does that compare with the line of sight distance? It's a measurement there of inflation of distance. And I'll talk about some potential inaccuracies with this approach. One is that geolocation techniques are pretty stinky. Okay, so you don't take any one geolocation result too seriously. But what we see here is that there's a stretch of about a factor of 1.8 here over the best path that you could have seen if you went just a line of sight to the routers. And some other caveats are that in general, when we look at a trace route, number one, we can't identify all the router locations like this one, so we just ignore them. And number two, the path between any 2 points, the fiber doesn't necessarily follow line of sight, right? These fibers are laid down where there are roads and railroads, and those things will be designed to avoid mountains, and they may have to go out of the way. And so what you see is that the actual ping time, or TCP SYN-ACK time, is worse than what you might have hoped for given the routers that you see on the path. Now, there are some networks that will give you full details about all their fiber links, including the distances that those fiber links travel. And one thing that I learned when I was doing this study is that they don't actually send a truck out and measure the fiber distance. Okay, what they do is they send a light signal back and forth, and they measure the time, and they know the speed of light in fiber, and they give it to you that way. So we actually have the distances and the times. So we can look at a network like Internet 2, and we can say, okay, this is the actual fiber map for Internet 2, and let's compare the measured distances in the fiber with, say, the best roads you could take in the US. How close does the fiber come to the roads, and how close are the roads to line of sight? And so what's interesting to me is that, first of all, the road system is really pretty good compared to line of sight. So we looked at all pairs of cities in this map that you just saw, and we computed the shortest drive, and we compared the distance with line of sight distance, and here's the CDF. It's like, 60% are within 20% of line of sight. So on the roads, you're pretty good. So if you take Internet 2, the fiber distances are longer. Okay, they're not as, it's much sparser. You could see that. Now, this thing doesn't compare to the highway system.
Hey, Bruce,
Yeah.
does that change if you go to freeways instead of roads? It seems it must.
I don't know. I bet we just did Google Maps and asked it for the shortest distance. So
Okay, so
it,
they would prefer freeways probably.
no, but we asked for shortest
literally
distance.
shortest
Yeah. So we didn't really try that. If you change to just freeways, we're not measuring, like, we're not asking, how fast at 55 miles an hour or whatever.
Yeah, no, I get that. I just, in my head, I think of once you allow all the back streets and stuff,
We probably
very rich. But
we probably did do that.
yeah.
Okay. So the main point, though, is that the fiber, it's not really line of sight. The roads, if you can take the back streets, is pretty close, but the fiber's not. Now, one thing, though, is that's just one network. We have some other networks in Europe, GAONT and ESNet. They're about the same, okay? A natural question, though, to ask is, all right, what if we instead, of course, if you just look at one network, you might not expect it to cover all these cities very well in the US. What if we could take all of the fiber in the US? And, I'm going to skip this. And try to address that question, okay? Or more generally, how could we build a speed of light internet? And the first thing we could ask is maybe a simpler question, which is, could we build a speed of fiber internet? Okay, let's give up on the factor of 1.5, speed of light in fiber. That'd still be pretty darn good if we were only off by 50%. Unfortunately, and sort of frustratingly, it appears that most of the research on modifying the speed of light in fiber is going in the other direction. People are working really hard to make light travel slower in fiber. All right? Why would anyone do that, you might ask? It's because in all optical switches, the way that packets are buffered is they just go into a spool of fiber and they fly around until like some kind of switching operation can be set up, and then they go off. Right? So we got to get those guys to stop and work the other way. But for now, it's a factor of 1.5. And here's a map that was produced by Derigen, Barford, Summers, and Willinger. It appeared in a paper in SIGCOMM 2015. And what they did was they went and they surveyed a bunch of internet service providers, and they asked them about the fiber conduits that they use in the United States. And they've produced a map, and it shows pairs of cities connected by conduits, and they made this data publicly available. It gives an estimate of the length of the fiber, of the conduit in kilometers, and it also, they have a list for each conduit of which of these approximately 20 internet service providers are using that conduit. This is what the map looks like. So it's much more dense than the map we saw a moment ago that just covered the Internet 2 network. So you might ask, all right, if we could use this fiber as efficiently as possible, if we always took the shortest path in the fiber, how would that compare to line of sight? And the answer is pretty good. So what we did was we looked at all pairs of cities with a population of greater than 20,000 people, and there were 249 of them on this map. And then we asked, okay, what is the length of the shortest path through the fiber compared to the line of sight distance? And we found the inflation over the median was only 20%, and even at the 95th percentile, it was only a factor of 1.5. Well, that's pretty good. That says that if you could really use the fiber efficiently, we could get this down. If you take 1.2 times 1.5, that's about a factor of 1.8. Whereas what we really see in practice is a factor of 3.2. I had this idea that I would just go to Akamai and say, we're going to start offering a speed of fiber application layer overlay network routing service so that we can give people roughly 1.5 or 1.8 times the latency of the speed of light service. And so I did a study where I looked at every single one of the conduits. There are over 1,000 in the map, 1,080. And I asked, on how many of those does Akamai have servers in the cities at both ends? And at first I was pretty optimistic because I found out the number was 51%. Okay, 51%. Now, partially the number is a little bit low because you do have places like this and this where these are, maybe we're not going to necessarily put servers in every 20,000 population town that's somewhere on the middle of a fiber. So it's not surprising that it's not 100%. And then we did experiments where we did pings and trace routes across all these conduits. For every conduit, we did pings and trace routes between all pairs of server on one network on one side and server on another network on the other side. And the results were really disappointing. We only found that we were able to send traffic across 7% of the conduits directly. Okay, so no way could we build an overlay network. So I started looking into this, that is without more deployments. I started looking into why is this happening. And first I found that in only 12% of the conduits did we have servers on both sides of a conduit, and the servers on both sides were actually on the same network. They're both hosted on the same network. But even of those, I found that when you did the trace route or the ping, it oftentimes didn't use the conduit. It went some other way. Even though it was there, it didn't use it. So then I asked, okay, for what fraction does Akamai have servers on both sides? Servers are on the same network, and according to the Intertubes data set, that network is supposed to use this conduit. And the answer was 3% of the conduits, okay? But then when I actually looked at whether we used that, whether the packets went across the conduit, it was more than 50%. I was surprised it wasn't 100, but it was more than 50. So it seems like the key to doing this, if you wanted to build, it's not going to be easy, but if you wanted to build an overlay, you would have to identify. It's a huge optimization problem, but in the end, it's hard to force a packet to go across a conduit. Because of routing policy, you're going to pretty much have to look for places where you can host your machines on the same network that's using the conduit and hope that their IGP, their interior gateway protocol, is basically doing shortest paths, and that you'll be sent across that conduit because it's the quickest way. So that's part of an ongoing study. I would like to produce a number for Akamai that says you need to deploy in 500 places, and here they are. And I haven't finished that yet. Okay, now I mentioned the financial traders. What I'm going to transition to is talking about how we might build a true speed of light network. And one of the advantages we have in trying to come up with a straw man design is that there are people out there who are very actively building these things already. And in fact, there have been 13 parallel networks built between New Jersey and Chicago for use by financial traders. And the basic idea here, the basic application is the financial traders learn about an order to buy something in Chicago, in New Jersey, and then they have a faster network than the one that carries the order, so they transmit that information to Chicago, where they buy that object out from under the person who's issued the order, and then they sell it a little higher. Okay, that's the whole idea. And so a group built a fiber-based network, and that fiber-based network, the first one, which is shown in red, the round trip time was 14.5 milliseconds. This includes the factor of 1.5 slowdown for the speed of light in fiber. And also you can see that the path was not that straight. So then another group built a better fiber network, and they got it down to 13.1 milliseconds. And you know, as soon as you build one that's a little bit faster, everybody switches to you. You get all the traffic, right? So the next guys came along and said, all right, that green fiber path is pretty good, line of sight. The way we're going to beat it is we're going to switch to microwave transmissions. And they built this, the red dotted network, which it's even more line of sight, plus they don't have that factor of 1.5 slowdown from the fiber. They got it down to 9 milliseconds. And then the next network came along and they straightened out the path in Pennsylvania. And they got the time down to 8.5 milliseconds. So they're up to 90% of the speed of light. And the nice thing about this is that it's now pretty easy to go and learn about the technology they used, for example, to find out what are the bit rates of the radios, what's the maximum range of the radios, what does it cost to license spectrum, and so on. And our co-authors, Greg and Anthony, have been consultants in that industry, so they had all this data. They also have big databases showing where are all the towers in the United States that you can put microwave transmitters on, and what is the topography, I think that's the right word, of the United States look like? Where are all the hills and mountains that you would have to worry about? And for the radios, you know, what kind of clearance do you need? Those guys know all that stuff. And so we explained to them what we wanted to do, and they put together this map. This would be a map that we take the 84 largest cities in the United States. And we assume that the traffic flowing between any two cities is proportional to the product of their populations. This is not a perfect model, and people have suggested a lot of different ways to model how much traffic flows between cities. Sometimes people will add some penalty for the distance. Understood. The model's not right. If you were really going to do this in practice, maybe you go to a large ISP and you find out, you know, what the actual traffic is. But that's the model we used. And then we ran a big optimization algorithm where we fed in all of the available towers, and for each pair of towers, we could determine whether or not it was possible to directly link them with microwave transmitters. And we kind of did sort of like simulated annealing approach to throwing links in and modifying links in order to try to minimize the lengths of the paths between cities. And so we found out with about 4,000 point-to-point links, over all pairs, the median inflation was about 1.03, and the 94th percentile was 1.5. So, I mean, it kind of goes back to Vern's question about the road system. There are tons of towers all over, and if you can use any of them and just lay out the paths you want, you can do pretty well. Where we had large amounts of traffic that need to flow between some pair of cities, we sometimes put in parallel links, that is, parallel frequencies were used between the same set of towers. So that capacity is built into this model. This includes multiple links sometimes between pairs of towers. The total aggregate capacity, just summing up the capacity of all of the links taken together, is 150 gigabits per second. That's not that much. So that's about something on the order of 0.1% of the non-video traffic on the internet. So it's a tiny amount, okay? Certainly more than the financial traders need. It's a small amount. You could scale this up, but I'm going to tell you, based on this estimate of capacity, how much this would cost. At $75,000 per link, this would cost $300 million total to deploy. This includes labor, includes everything, includes the radio. And now this number, I'm not completely sure where we get it, but that's sort of maintenance for the radios. Maybe that's low. If we amortize the deployment cost over 5 years, this comes out to 16 cents per gigabyte. Now that sounds high. You certainly would not want to pay that at home, but it's not that high compared to your cellular data plan. It's kind of comparable. So you could offer a line of sight, almost light speed network for the cost of cellular data. Ballpark. Maybe that's not surprising. I mean, cellular data does kind of the same thing. So I wonder what my next slide says. I've been thinking a little bit also about the business model for this. Like, okay, maybe you could do it, but how would you actually pull this off in practice? We know how much it would cost. What would it take to bring up a business? How would you operate a speed of light ISP? So the first thing is, you saw that the bandwidth is low. So there's no way, and the cost is high, there's no way you would go and sell to somebody just the speed of light network. Probably not. What you'd probably want to do is bundle this with some traditional service where most of the data, like the video, would go over fiber, but select data, maybe acknowledgments, maybe for certain applications like games, it would go over the speed of light network. You might go to content delivery networks and e-commerce website and say, you should peer with us. You should put your servers into our network because we're going to get the data to the end users as fast as possible from your server to our end users. You would have to solve this problem of, we can't have end users manually trying to figure out which traffic goes on which network. We'd have to build tools for doing that. Here's an interesting routing strategy difference between a traditional network and a speed of light network. So traditional networks use a strategy called hot potato routing. When a packet arrives on a network like AT&T, they look at where it's going and they find the closest place on AT&T's network where they can dump it out off their network and give it to someone else. Because they want to do the minimum amount of work, right? They don't really care about the shortest path for that packet. They just care about how can I minimize my cost. A speed of light network would say to its customers, we do cold potato routing, okay? So yeah, we're charging you more, but we promise you that once your packet enters our network, we will carry it as far as possible to its destination before we drop it out. Because we can do that at the lowest latency for that distance. And so that, of course, you pay a premium for that, but it's the reverse of the usual routing strategy within the network. Now, I think I'm about done. I think, though, it's always good to think about, okay, what's next after this? So actually, this has been contemplated before. Can you do better than a speed of light network? And in fact, we draw motivation from Spaceballs, where Dark Helmet declared, light speed is too slow. We'll have to go straight to ludicrous speed. Okay, thank you.
so I'll bring the mic to you.
Thank you. So at the beginning, you showed us that the ping delay is maybe a factor 3 beyond
Yeah.
light speed, but the typical application, it's a factor of 35.
That's right.
Now you spent 90% of your talk trying to speed up that factor 3 of the ping delay, while it seems to be much more beneficial to actually do something about the application and the protocols and all of that, because that's where the delays are. And oh, by the way, I expect an answer in 20 milliseconds because sound will take about 20 milliseconds to travel 5 meters.
You're right. Okay, you're right. As you say, there's like this factor of 10 that's coming from the protocols. And that's because there are 10 round trips. That is also being worked on. Google is a leader in that area. So Google is figuring out how to remove, say, the three-way handshake by doing TCP caching. So you remember, you've seen this client before, you don't have to do that. They're working on TLS caching. Those websites were all, we didn't do any secure connections there, but if you actually waited for bytes to be delivered securely, there's even more handshakes. So that's a ripe field. And it all boils down to removing round trips. In some sense, it's easier too, because if you can just change the software, you don't actually have to deploy new hardware. So I think that's fair. I think this is one of these examples, like I think Pascal said of Pascal's triangle, you know, there's room for everybody to play. But you're right.
How concerned are you about buffering in terms of increasing the delays in today's internet?
So we've done a bunch of studies, and we're not seeing any buffering in the core of the internet. The amount, and the way we tell that is we do studies, the same measurements over and over at different times of day, and they don't vary. That's evidence that there's not much buffering going on. And the variance, at any kind of distance, the kind of delay you see at a router processing packets or waiting for a packet to go through a queue, it's negligible in all of our studies. Now, last mile is a different issue. Okay, in the home, or if you're on the a cellular data, there's all sorts of bad stuff happening. But in the and that's kind of orthogonal. You have to upgrade the technology of the last mile, or you don't see the benefit of upgrading the core. But in the core, it's not a problem.
I have a question. Could you maybe show us the map of your computed network, maybe 2 slides or 3 slides back? So one thing that looked interesting, seems like if you're in the West, you get the shorter end of the stick, and that a whole bunch of connections head straight to further on the East Coast to then come back. And I was just wondering if you could give an intuition between something that was noticeable in this, the northwestern part. And is that because there are no towers, or?
Okay, no, it's not about that. It's just because, there's a main effect going on here is there's a little bit of an optical illusion. So if you look at this path from Portland to Chicago, say, okay? That's got this big dip in it, and it looks like, that's not anywhere near a line of sight. That's actually only about 10% longer, right? It's confusing, but some of these things that look like they're suboptimal, they are, but they're not as bad as you think. So there's that effect. And I think also it's based on, these numbers are based on population. So that's just where the links go. I don't know what to say.
Move to a bigger city.
By the way, if there's whole sections here where you're not on the map because there's no population. Interestingly, the Chicago to Seattle is currently being built by the financial traders. That's the next line of sight network. And that might seem strange to you because Seattle is not a financial hub. So why would they do that? Why would the financial traders build a high-speed network from Chicago to Seattle? Yeah, it's because the cables from Tokyo land in Seattle. So you can get to Tokyo fastest if you can get there from New York or Chicago fastest. Yeah.
Excellent. Any last questions? Then let's thank our speaker
you.
again.